Let's take a look at exponential growth and decay. Um, the generic formula for it is A of t, and that is the amount of whatever the substance we're doing. Maybe it's bacteria, bunny rabbits, some sort of radioactive substance at a certain time t is equal to A naught. So that A0 is pronounced A naught, and that just is your starting amount or like initial deposit. E, Euler's number. K is a growth or decay constant. So it's kind of like the interest rate in the continuously compounded interest problems. It can be negative, positive, and it doesn't have to be a decimal. So there's a little bit more flexibility with that. And then T is time, and when we were doing the continuously compounded interest problems, it was always in years. Time can be in days, it can be in minutes, hours, years, so there's a little bit more flexibility. So a lot of times we're going to be asked to find the amount at a certain time, and in order to do that, I'll need to know my initial amount, or my starting amount. That's my A naught. So the initial conditions, or your initials, or what you're starting with. K is a growth or decay constant. If it's negative, it's going to be decay. Positive, it's going to be growth. And then the time has more flexibility than it does in the continuously compounded examples. Okay. And let's go ahead and move on to the next slide here so you get the idea. Alright, so let's suppose, we'll speed this up a little bit. Okay. So let's suppose A of t is equal to 25e to the 0.75 t, and this models the number of bacteria in thousands on a peach that was left outside this morning at 7 a.m. In case you're asked as you're going through your homework, your growth or decay constant K, in this case would be, it's already given to us, so it's 0.75. So that's good for us. That means that's less work for us. We don't have to go find like the interest rate or something like that. And then they can ask us a number of different questions, and it's very similar to continuously compounded interest problems. So let's see what they want is, how much bacteria is there at 7 a.m. and that's when the peach is put outside, so that would be that when our time is equal to 0. And that's the most straightforward. We just go ahead and we plug 0 in, okay, and then we should get 25 e to the 0, and that's just 25 because e to the 0 is 1, and our units are in thousands, so it would be 25,000. So a lot of bacteria on that peach. Another question they can ask is, how much bacteria at 2 p.m.? Okay, so here we have to think a little bit. So if time is 0 at 7 a.m., then 2 p.m. should be probably about 7 hours later. So our time is now 7, and we just got to plug it in, throw that into your calculator, and that's all you got to do for that. Just be careful about how you enter it into your calculator. Be with the parentheses and all that. So when I plug it in the calculator, I get 4764 approximately, and that's in thousands, so we'll throw on 3 extra zeros there. So what we really have is, after 7 hours of this, who knows if this is realistic. It's just a practice and application here. So after 7 hours, we have 4,764,000 bacteria. So I don't think I wanted to eat that peach in the morning with 25,000. You certainly don't want to. Now you're almost certainly going to get sick. Bad kind of bacteria. Okay. Those are the pretty straightforward ones. The other type of question they can ask you is, what time is something going to happen? So let's say what they ask us here. So one of the common questions they'll ask is, how long does it take to double? So if we start out with 25, double that would be 50. Okay. And we want to know what the time is. All right, so we're going to plug it in. 50 is equal to 25 e to the 0.75 t. So this is exactly the same process as, what is the time required for our money to double? Exactly the same thing. We'll have an interest rate. We'll never know everything except for the time. So it works the same way. We'll divide both sides by 25. And we get 2 is equal to e to the 0.75 t. And to solve for an exponent, we'll use the natural log to bring that exponent down. And because e and ln are inverses, we just get the 0.75 t. Okay, and we'll go ahead and divide both sides by 0.75. And our time is approximately, let's make it in a kind of how I would put it in the calculator, 0.92, and that's in hours. So if I wanted to get an idea of minutes, I'd multiply it by 60, and about 55 minutes. So it takes that bacteria about 55 minutes to double. All right. And those are some of the pretty basic examples. I'll make 2 more videos where we do some other things. One with a population of bunny rabbits, and another one with some sort of radioactive decay and some different problems they might give you.